Okay guys, so I'm going to go through this pretty nice and quickly. This is your Chapter 15 practice test review, and we're going to start with some true and false, like always. So the first question says, collisions between reactant molecules do not always lead to the formation of product molecules, and that is true, because as we saw with those energy graphs, in order for a reaction to actually happen, the collision has to have enough energy to create the products, and sometimes it doesn't. So not all collisions result in reactions. Number 2, reaction rates generally increase as a reaction proceeds. They actually slow down because as you get more and more product being made from the reactant, what happens to your reactant is that it's decreasing. So if the concentration of your reactant is decreasing, that means that the reaction rate is going to slow down. Okay? The rate of a chemical reaction is directly proportional to temperature. Okay, the hotter something is, the faster the reaction will happen because the particles are moving faster, which means they will collide with one another with more energy and more frequently, which means the reaction rate will increase. Dynamic equilibrium is established when the rate of the forward reaction equals the rate of the reverse reaction. It has nothing to do with zero. Remember my analogy with the two schools. 3 individuals are leaving the PHS party, 3 individuals are going into the PHS party. That's when we're in our dynamic equilibrium. Because at one point in time, you don't notice a difference in population size, but it's not like nothing's happening. There's a constant leaving and constant coming back in to the party. 5, when dynamic equilibrium is achieved, the rate of the forward reaction equals the rate of the reverse reaction. It has nothing to do with concentration. The concentrations most of the time won't actually be equal. The only time they'll be equal is if your KEQ equals 1. Otherwise, either your products will be favored if your KEQ is greater than 1, or your reactants will be favored if your KEQ is less than 1. 6, it is necessary to have a balanced equation. It's necessary because you're using coefficients for your equilibrium expression. And if you haven't balanced it, you're lacking those coefficients which are necessary. 7, the larger the equilibrium constant, the greater is the concentration of the products. Remember, products go up above, so the larger your equilibrium constant, the more products you have. The smaller your equilibrium constant, the more reactants you have. Okay, 8 is true. 9, since your KEQ is so small, that means that your reactants are going to be favored. If it were 2.0 times 10 to the 8th, then yes, your products would be favored. 10, increasing the volume of a system below causes the reaction to shift. Okay, so if I increase volume, what that means is I'm decreasing pressure. And remember, I've got to move from, if I'm decreasing pressure, I'm moving from the side with fewer number of moles of gas towards the side with more. And if you notice, this wouldn't count as a mole of gas because it's a solid. So here I've got 2 moles on this side, 1 mole on this side. So I'm going to scoot over to the left if I decrease pressure. 11, in an exothermic reaction, you can consider the emitted heat as a product, like here. If I put heat on this side, that means that heat is being used up, which would make it an endothermic reaction. For 12, all of those apply. Those all cause an increase in reaction rate, which we talked about in class. For 13, the reason why reaction rate decreases over time, I've already said this, as you make more and more product, that means you have less and less reactant, which means due to the decrease in reactant concentration, you will have a slower reaction rate. Okay, so that's C. Which of the following is true about a chemical system in equilibrium? D. Okay, the reaction rate stays the same. 15, a chemical equilibrium exists when the rate at which the reactants, this is the same definition, nothing new. Here, remember, it's products over reactants, so it's going to be C squared times D cubed all over A squared times B. So your answer is D. Make sure you're not adding or anything. Which equilibrium constant represents a reaction that favors the formation of products the most? So that means if products are being favored, that means I want the largest number there, which is B. If I want one that favors the reactants, then it's going to be D. 18, Le Chatelier's principle, this is just a definition. When you have a disturbance of equilibrium, it's going to shift to try and minimize that effect. Okay. For 19, I'm asking what causes a shift to the right. So let's look. For N2O, if I increase N2O, that's going to cause a shift to the right. Okay, so that's good. If I remove O2, it's going to cause another shift to the right because I've removed it. So it's going to shift over to reestablish equilibrium. And if I remove N2, it's going to shift to the right as well. So D is your answer. Okay. For here, If I add Cl2, I'm going to shift to the right. If I add COCl2, I'm going to shift to the left. If I add CO, I'm going to shift to the right. I'm hoping this is getting easy by this point. As soon as I'm talking about volume or pressure and I'm dealing with gases, I've got to add up the number of moles. So I've got 1 here, 1 mole of gas, 1 mole of gas here. You just look at the coefficient, so that's 2 total, and then 1 mole here. And so if I increase volume, that causes a decrease in pressure. So I'm going to shift to the side with more numbers of moles of gas. So I'm going to shift to the left. If I increase pressure, I shift to the side with fewer, so that's to the right. If I decrease temperature, I'm going to shift to the right to make up for this loss of heat. All right. If I add I, so I is here. If I add I, I'm going to shift to the left. If I remove I2, I'm going to shift to the left. If I decrease pressure, so again, I'm increasing if I decrease volume, which causes an increase in pressure, this is 1 mole of gas, this is 2 moles, so if I'm increasing pressure, I'm going to shift to the left because I'm going to the side with fewer number of moles of gas. If I increase temperature, I'm going to shift to the right, and if I decrease pressure, that means I'm going to shift to the side with more number of moles of gas, so I'm going to shift to the right. Okay. What I'll ask you to do for all equilibrium problems is write out your equilibrium expression first. So it's concentration of SO3 squared divided by concentration of SO2 squared times your concentration of O2. Now I give you all the numbers here. Sorry, I crossed them out. They're not crossed out on your page. And you just plug them in. So I know SO3 concentration is 11.0, so I'm going to square that. Divided by, I know my concentration of SO2 is 4.20 squared. I don't know my concentration of O2. You can write this as X, guys. I kind of prefer writing it like this, though, concentration of O2. And then I tell you your K equilibrium is 798. So math-wise, what you have to do, you have to you're going to cross-multiply. I always cross-multiply. So this times this, so it's 4.2 squared, times your O2, equals 11 squared, which is 121. Divide both sides by the 14,000, and I get 0.00860 for sig figs. And then you need units for concentration, which are molar. Remember, for KEQ, you don't have units, but for concentration, you do. 24 is very similar. First, I asked for your KEQ, so it would be H2 squared, concentration of H2 squared, times the concentration of S2 divided by H2S squared. And then I just plug and chug. I know the concentration of H2, which is 2.74 times 10 to the negative second squared, times the 7.54, which is your concentration of S2, divided by concentration of H2S. And I'm solving for KEQ. I needed 3 sig figs, so here's my answer. And look, I don't have units. Okay. Again, this should be old by this point. This concentration of this, your products over the concentration of your reactants. Okay. And then you just plug in numbers. In this case, I'm asking you to solve for this. So to solve, you're going to do the 14.50 times this times that, and you get 0.15114. You want 3 sig figs, so this is your answer, and your units are molar. Okay. Which arrow represents the activation energy of the forward? So remember, your activation energy is just the hill you have to get over. So that would be B. Which arrow represents the activation energy of the reverse? Well, this would be the reverse. I'm here, and I finish up here. So there really isn't an arrow that represents this. So instead, what I could do, C minus D. So by subtracting, I'm just getting rid of this area. That gives me this reverse activation energy. So C minus D. Which arrow represents the energy of the reactants? That's A, whatever energy they start at. Energy of the products is D, and since it loses energy, energy is released, it's going to be an exothermic reaction. For this one, since it's gaining energy from the reactants to the products, it's endothermic. Okay. The reactants are here, the products are here. The activation energy for this reaction, I would take the 250. Okay. The 250. And subtract 50 from it, right? Because the 250 represents a whole line all the way down here. So this distance right here, which is the activation energy, would just be 200. How much energy is released or absorbed? So it's just the difference between your reactants and your products. Products end at 100, reactants start at 50, so it means that you absorb 50 kilojoules, which is consistent with the statement that it's an endothermic reaction. And you're done.